The homework set 5's due here. And try to hand it in by the end of class. And after class, I have the solutions here, hard copy. And later on today, we'll make the electronic copy, which is a copy of the same, available. And that's because there's a midterm on Thursday. And that's Thursday, February 17th. Here, for those who don't know where here is, it's McCullough 115, and it's from 11 to 12:15. And it will cover chapters 1 through 6. So on. All right. Last time, we showed that H is less than the roof code expected description length is strictly less than the entropy. And in particular, if we put a star here, meaning the optimal code, the Huffman code, that will lie between H and H plus 1. And then we had L sub n greater than H of X super n over n less than H of X super n plus 1 over n by encoding blocks of x's of length n. And now if this is stationary, I won't put if stationary, this is a recap of what we've already done. This goes to the entropy rate of x, which is defined, and this converges to the entropy rate of x because the 1 over n term plus 1, because the 1 over n term goes to 0, and therefore L sub n, the expected description length per symbol of the x text, converges to the entropy rate x. So that's a very satisfying answer to the question of data compression. How much data compression can we get? In this case, this is the expected description length, and it goes to this. Now you can also show that the actual description length goes to the entropy rate, and you do that by noticing that minus 1 over n log p of x1 through xn for ergodic processes converges to the entropy rate. That's known as the Shannon-McMillan-Bryman theorem. So not only is it true in expected value, which we've shown, but it's true with probability 1 for ergodic, stationary ergodic processes. Now, we also looked at Huffman coding. And that's the way to minimize the expected description length. Now, it's interesting. Huffman coding is really a greedy algorithm. You combine the smallest two probabilities, forming now from n, let's say from m probabilities, now you have m minus 1 probabilities. And then you combine the lowest two on that list, forming a shorter list, etc., 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 until you're down to something with probability 1 as you combine that. So you're always combining the least two probable symbols at that stage of the reduction. And then the proof of optimality of Huffman coding, which has a nice symmetric proof in the text, is to say, well, I know how to encode a random variable that takes on only two values. I assign 0 to the first value and 1 to the second. That's optimal. And then you say, oh, when I expand one of those nodes, the one that had been collapsed, as I kept reducing the probability strength, as I expand that, I now have an optimal code for 3 outcomes. Expand the appropriate one, the one that had been collapsed before. It's now optimal for 4 outcomes, etc., blah, 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 until you get out. And you now know that the Huffman code is optimal for probability masses P1 through Pn. We talked about 20 questions. So if you have P2 to the 20th, then your first question should be not the one-bit question that makes these probabilities as close to a half as possible. That is, what subset has passed. That would be Fano's wish when Huffman solved it. But it would be, you do the Huffman coding on these, and then look at the first question, and the things hanging off the tree is the subset you ask. And so your first question would be, is the object the one corresponding to the top branch of the tree? Or equivalently, if your Huffman code turns out to be this, 0, 1, 0, 0, 1, 1, etc., your first question would be, does the element, the index I, have associated with the code word that has a 0 in the first place? So that would be your first question. And then you keep asking questions until you've reached the end of a code word, in which case you have now determined what the object is. By the way, let me interpolate something here. We might talk about alphabetic codes or slice codes. You know, I would like to arrange it so that all these start with a 0 and all these start with a 1, where the p's are monotonically decreasing. In other words, I would like to ask a question like, does it weigh more than an elephant? You know, that kind of question. In this case, it'd be, is the index higher than 78? But a Huffman code might give you all scrambly zeros and ones here. So can I find a code with the Huffman code word length, which gives me the ability to just keep asking questions like, is the index greater than this critical number? Then the next question, is it greater than this critical number? And then, is it greater than this one? And so on. That's somehow simpler, because you really don't want to ask a question about an arbitrary subset here. There are just too many of them. And so it would be hard. Is that, you can hand it in there if you want. Yeah. Good. And the answer is yes. You can always do that, because Huffman will give you L1 through L, in this case, 2 to the 20th. And then you take these lengths, and these are, let's order them. Let's see, less than or equal, less than or equal. They're ordered this way because the P's are ordered this way, P1 greater than P2, etc. So the L's are ordered that way. And then you just find the appropriate, the first branch on the tree. So let's see, 0, 1, 0, 1, 0, 1. And suppose L1 equals 2, L2 equals 2, L3 equals 3 through, L, whatever it is. All right. So you just assign this. This is for P1. There's code words for P2. There's code word, this is for P3. Here's P4. P5. P6. And now we've unscrambled the code words that you get from a Huffman code and found an equivalent code with the same code word lengths assigned to the same probabilities, but now they have this very agreeable property that your first question is the index 2 or less? And your second question is the index 4 or less? And the third question is the index, if you're here, 5 or less. So you see the advantage of doing that. All right? Then we looked at the cost of the wrong code, wrong distribution, and delta L is equal to D P Q and plus 1. So if the true distribution is P and you design your code for distribution Q and you use the ideal code word length, maybe round it off to the nearest integer above, that's where the plus 1 comes from, it's cost you an extra expected description length of dpq. So already we see we have a theorem that says how important H and the entropy rate are. They come up naturally as the answer to a data compression question. And then we see how natural relative entropy is. It comes up as the answer to